we can say we have some extraction for using to make heat exchange with the output to condenser, and some others continue for expansion and so on. It's not go through same like the previous, like this. Let's see. We can see from initial point like this, 4. From 4 to 5, you see 4. Where is 4? Here. Not down as a before. No, starting from here. So as you see, we minimize the Q added as we can. So from 4 to 5, this boiler, okay, as regular it should be this 4. It's not here, it should be something down, okay. But according to the modification I make it here for regeneration and so on, I going to end for the temperature with high temperature, okay, not low temperature. And after that the expansion happen from 5 to 6 here, from 5 to 6 expansion happen. And also on the same time 7, 6 and 7 is the same condition. 6 and 7 same condition. But what happened, I take some from this way and take some from this way. I take this amount to make reheat and back to the second stage of the turbine, and take the another amount is going to make regeneration with the flow coming from the condenser. Let's see what is coming from the 6 here is going to reheat and back to low pressure turbine. So you found 6 here, this 6 going to up here to increase temperature again for 8, and from 8 expanding to 9 like this, and from 9 bathing through condenser to be saturated liquid. I am see now this one is fully liquid with low temperature, is good. But actually still we have some amount from this is high pressure turbine 7 is going to mix with what is coming from the condenser. What is the reason? The reason is increase the temperature going to boiler, okay, to decrease heat added. So what's coming from here, just I make bump it up to the same pressure coming from 7, because to mix the two fluid it should be the same pressure. So the pressure line here is the 7. This is the pressure line for the 7. This is the pressure line for the 9 and 1. So I make it bumped here from 1 up to 2. What is 2? 2, it is the same pressure line of the 7. This 7 and this 2. So it's going to mix together. 7 and 2 is direct mixture, not heat exchange, just direct. So it mixes it together at 3. Then after 3 is going to bump it again to the bump required for the boiler, high pressure line, okay, for from 3 to 4. Clear? This, as you see here, is a mix between regeneration and reheat. Brighton cycle. Take first. Breath.
Go back to the previous slide. Previous to previous.
Yes.
Previous.
I hear you.
Yeah. And the superheating cannot be possible between the boiler and the turbine.
What's for boiler and turbine?
In between boiler and turbine, superheating is not possible.
Between boiler and the turbine. Boiler at 0.5?
On the left side.
This one? What is
yeah,
here?
I am telling that if we superheat the saturated steam, which is coming out from the boiler and going to the turbine, before going to the turbine, it's not possible.
This one? This
yes.
already superheated.
Okay, it's already separated. Okay.
Yes.
Okay.
But this is the output from turbine. So I already collect the energy I need, but still have energy. So instead of just release it in the surrounding, no, I make it here like heat exchange to increase the temperature coming from one.
We are preheating feed water basically.
Yes, feed water, but this feed water close.
Yeah,
this feed water open.
Yeah, exactly. Okay, thank you.
Welcome. Brighton cycle. Uh, if I tell you it's important, it is less. It is higher than important. Okay. This cycle is coming normally. Not all time is ask for the total request for the cycle, but just ask for element. Maybe it's coming as a total shape, but just focus for one element. Okay. I see. I received one question from this type for recent question from maybe from 2 weeks, something like this. But still, I not added. I will add it for you for exam 5 or 6, related for direct for Python. Okay, it's very important question. Let's see describe for this Python cycle. As I tell you, as a regular cycle, it's have 4 elements, but here this one as a real one for gas turbine application is only 3 elements, and this said is open cycle. But just going to describe first the closed cycle here: compressor, heat source, heat sink, this turbine. Normally for gas turbine, which is the left side here, we will focus for this one, which is open, this the regular one and application for gas turbine, this compressor, this turbine, this combustion chamber. Normally we consider for the exam, consider the media inside here is air. This is the regular question coming the exam, not air and after that exhaust gas. We consider as all as air. Start point one here, fresh air, compress this air here, isentropic compression. Isentropic compression. Almost all cycles we study here, turbine, compressor, pump, isentropic process, whatever compression or expanding. Two here is after compression going to combustion chamber with mixed to fuel. Output is products and sometimes we said exhaust gases. This exhaust gases or product going to turbine with high energy here, high temperature is the highest temperature at all. This high temperature going to turbine to expand and they obtain work. This exhaust gas output. Actually, the compressor, it is working by connecting shaft between turbine and the compressor. Just only we need for compressor the starting, just the start. Only start for this compressor to start the process. After that, the work required for compressor is totally fed by turbine. Okay. Here it's not the same Rankine cycle. We can cancel pump work. No, here compressor work it's not neglect. It's effect for the value. So it should be get work net, which is equal to work turbine minus work compressor. When we need to calculate work net, we need to calculate efficiency output over input. Output here work turbine minus work compressor. Okay. And what is the Q added? This is a part for Q added actually. Combustion chamber. Combustion chamber. Let's see describe this cycle, PV diagram and TS diagram. I will focus on diagram is better for me. TS diagram, as a no regular cycle, it's working this cycle between two pressure line. Okay. Normally the Q added and the Q rejected, it's happened during constant pressure. Some cycles it's not constant pressure, going to constant volume, something like this, but normally it's constant pressure. Same like this cycle, for example, it's working between two constant pressures. This line here from combustion chamber B2 and this line for heat sink here B1. Let's see the line for constant pressure itself, it's not parallel. This constant represent constant pressure, and this also represent constant pressure, but it's not parallel. When you're going left here, it's going to be close together, and when you're going right, it's going to be far. So this give you best results, which is here the for the right side is going to describe the work turbine. So work turbine is going to expand and obtain high work. But here in the left side, it is a small range, which is required work compressor, small amount required work compressor. Okay. So from 1 to 2, this point 1 here, maybe it's not clear. Where is this? 1 here, 1, 2, isentropic compression, then 2 to 3, Q added for combustion chamber, constant pressure, Q added constant pressure, then 3 to 4, this expansion, work expansion here by turbine. Okay, this is used for closed cycle, and if it's open cycle like this Brighton cycle, it's normally neglect. Okay, equation here important and it's not given in the exam, so it should be memorized. This equation, we have two similar equation, relation for 1 and 2 and relation for 3 and 4. Okay, this relation here between temperature and the pressure, what is this relation? T2 by T1 equal B2 over B1, direct proportional, to power gamma minus 1 over gamma. T2 over T1 equal B2 over B1, or equal to power gamma minus 1 over gamma. And B2 over B1 is equal RB. B2 over B1 is equal pressure ratio. So we can describe this T2 over T1 by this equation, RB to power gamma minus 1 over gamma. Here, for the analysis of cycle, any element or equipment need to calculate work or heat is equal to difference between two enthalpies. I forgot to give you things. For steam, water, refrigeration, H, it should be given because it's get it from tables, from charts. So should be given H. But he preferred to bring the Brighton cycle exam. Why? Because the media, it is air. So what is the advantage for that? Air, it can be follow ideal gas. So enthalpy, it's a function of temperature only, and this can describe by temperature direct. How can describe it? Difference between two enthalpies, it is equal to Cb difference between two temperatures. H1, it's like CbT1. H2, it's like CbT2. So H1 minus H2 is equal to Cb common factor T1 minus T2. So is only here we can describe H's enthalpies, the same concept of equation. Any element or equipment is equal to difference between two enthalpies, but we can describe this enthalpies by Cb delta T. This is the reason to coming a lot in the exam instead of the other cycles. Okay, because other cycle it should be need to give H. I see one question coming for steam before, but the steam problem here is not given H. So the only way from my side, I consider the range for turbine or the steam or superheated as approximately as a gas. So I can use it and apply it as a Brighton cycle. Cb delta T as it is, because I can't imagine what is enthalpy value. Otherwise, it should be given enthalpy. Clear? Because enthalpies, it is different or it changes according to the condition. So I can't to save it. It's not like gamma, it's not like G to save some values. No. It depends on the condition. Okay. So this is a reason for the Brighton cycle coming more than the other cycles. Okay. So, but equation not given in the exam. This relations T2 over T1 equal B2 over B1 to power gamma minus 1 over gamma. It's not given. Just to give you, for example, I don't remember the question, but it give you what I remember. He request the Q added for combustion chamber, Q added, and give you T3 and T2 not given, T2 not given. Okay, to calculate Q added Cb delta T, because it's delta H equals Cb delta T. So you need two temperature after and before. You have T3. How to get it T2? Get it T2. He give you some information of compressor. He give you some information for compressor. Give B1, give T1, give B2. Like pressure ratio you have, pressure ratio RB you have. You have T1. So by this equation, which is not given in the exam, we need to memorize. Give this one or RB direct and give T1. So we can get T2. Once you get T2, you can get combustion chamber. You see the sequence? Clear? But I give you the problem I sent you, or I put it in one of the exam we solved it together to know the values coming in the exam. By the way, T2 over T1 is equal B2 over B1 gamma minus 1 over gamma, or equal to RB gamma minus 1 over gamma. RB is B2 over B1. Okay. This isentropic compression for the compressor from 1 to 2. Let's go more. Here work compressor. Here you see CB delta T. This what? Kilojoule per kilogram. But if you multiply m dot, just going to be kilowatt power. That's it. For second case, for combustion chamber, the part for constant pressure heat addition, combustion chamber. So we can write it here, combustion chamber. Equal what? Q added is equal CB delta T, T3 minus T2, or this kilojoule per kilogram. If you have m dot, calculate Q watt. If you don't have, just calculate kilojoule per kilogram. Okay, so CB delta T. This given, this given. If this not given, going to back here to given from this relation. Similar to this, start from 3 to 4. 3 to 4 the same. T3 over T4 equal B3 over B4. What's B3? Is the same B2. And what's B4? Is the same B1. So B3 over B4 is the same RB. Okay? Gamma minus 1 over gamma. Normally in the equation coming T3 and get it T4 from the equation. And normally from here get it given T1 and request T2. So from here you need to get T2. From here you need to get T4. Turbine here, this work turbine is CB delta T after and T before. That's it. Turbine between 3 and 4. Clear? Kilojoule per kilogram, kilowatt if you multiply m dot. The fourth part, which is normally does not given because it's open cycle as a Brighton cycle for gas turbine is open, but if it's closed, we have a part for Q rejected. Okay, working it. This is equal to work turbine minus work compressor. Efficiency. After you substitute for the equation of efficiency and substitute for this one by temperature difference and so on, you get one of the best equation for efficiency ever. Very important, coming a lot. Efficiency for Brighton is equal 1 minus 1 over RB gamma minus 1 over gamma. What do you mean this? What you give you indication for this? In the problem, if only given RB pressure ratio B2 over B1, you can get what? Efficiency of the cycle. We don't need work turbine, we don't need work net, we don't need Q added, we don't need anything. If you given only RB, B1, B2, finish. 1 minus 1 over RB to power gamma minus 1 over gamma, you can get efficiency. From where this get? After this cancellation of the equation of efficiency, as you get it the relation only of temperature. Same like this one. Where is this? First one here. Here, this one. You see? This is the other one. Efficiency equal 1 minus T1 over T2. That's it. After different calculation here and simplification, you get 1 minus T1 over T2. What is 1 T1 over T2? If you go back here, T1 over T2 for the previous, here T1 over T2 is 1 over RB, because T2 over T1 is RB. So 1 over 2 is 1 over RB. This is what we see here. T1 over T2 is 1 over RB to power gamma minus 1 over gamma. Okay. Continue.
Yes.
Effect of pressure ratio on efficiency and the power. Pressure ratio, it is mean RB over R2, B2 over B1. So RB, when you're going max, this is coming theoretical. RB, when increase RB, pressure ratio increase, what happened for work? Work going to increase u- up to reach maximum. Okay, so increase up to a certain limit to reach maximum, then decay and decrease again. Okay, decrease again. So it's going to increase first, constant, or get maximum, then decrease. Okay, this for work. But for efficiency, the efficiency increase up to reach to the RB maximum. And once you reach to RB maximum, you get efficiency of Brighton is the maximum, which is in this case is equal to efficiency for Carnot, which is the ideal case. Clear? Read this first, please, and we're going to solve together. I just give you 30 seconds to read it. Okay, let's start. This Brighton cycle. This is like substitution for the previous equations. Brighton cycle enters, air enters, compressor at 0.1 megapascal. So we can give in here, right? B1, 0.1 megapascal, and T1 is equal 15 Celsius. Pressure leaving at 1 megapascal, so B2 is 1 megapascal. Maximum temperature Tmax 1100 Celsius. We need some other information for the pressure and some temperature, compressor work, water turbine work, efficiency cycle. Everything is clear, no problem. First, this P1 so is equal to B4. This P2 is equal to B3 as per cycle requirement. I'm just going to solve with another color here. And don't forget to change it to Kelvin. All temperature in T1 over T2 and so on must be Kelvin. For delta T, no problem, but for T ratios must be Kelvin. So this one, it will be equivalent to 273882. And this one, 273, which is this Kelvin. 7, sorry, 273, so this like this Kelvin. So now, what's the maximum of the cycle? What you expect? Maximum cycle, temperature. What's temperature? This T1, you have remaining T2, 3, 4. T3, 4. 2, 3, 4. Maximum temperature is the outdoor of combustion chamber. So if you expect it like this, you have compressor here, you have a turbine here. So 1, 2, 3, 4. So if we check, we found the 3 is the maximum temperature. So T maximum, it means 3. So now we can go to get T2. T2 over T1 is equal P2 over P1 gamma minus 1 over gamma. So in this case, what's gamma? 1.4 for air. So here we can check T2 is equal to T1, 288. B2, which is 1 megapascal by B1, which is B.1. Gamma minus 1 over gamma minus 1 over gamma, it means 1.4 minus 1 over 1.4. So it's something like is equal to 88 10 to power 0.4 divided 1.4. That's it. You get T2. T4, if you want T4, you can get it by the same way. T3 over T4 is equal B3 by B4 to power gamma minus 1 over gamma. So we can continue and get T4 if you need T4. If you don't need, okay, no need. Work compressor is equal CB delta T, which T? This compressor, this turbine, this combustion chamber. So compressor between 1 and 2, so it's T1 or T2 minus T1. That's it. From where CB is constant for air, same like CB, same like gamma, 0.718 kilojoule per kilogram. This for air. So two temperature we have and CB we have. Finished. Work turbine is a range between 3 and 4. So it's CB T3 minus T4. So still T4 coming from this equation. So we need to calculate it first from this equation. Okay, which is T3 is 1373 divided by T4 is equal to 10 to power 0.4 over 1.4. From this one can get T4. Efficiency, you have different types. Is different between two work turbine minus work compressor divided by Q added, and in this case you need to calculate Q added, or as a famous one, 1 minus T1 over T2, which is equal to 1 minus T1 is 288, and T2 get it from here. That's it. But if you don't need to calculate T2 and there is no required here anything, you need efficiency. Okay, it's easy. Eta is equal 1 minus T1 over T2 is 1 over RB to power gamma minus 1 over gamma. And do you know RB? So is 1 minus 1 over 10.4, 1.4. So we can get efficiency direct if you know RB without any previous calculation. If you have any question, tell me please.
This gamma equal to 1.4 is for the air.
For air, yes.
Yeah.
Normally, question for this is for air. So it's better. I advise you to save gamma CB. It's better.
لو سمحت يا دكتور، هي ار بي ب 10 ازاي؟
RP is equal to 2 over P1, which is equal to, where is P1? 0.1 over 0.1. This megapascal and this megapascal. So it's similar units, no need to change unit from megapascal to pascal. The ratio up and down is the same. So let's keep it as it is, megapascal, megapascal. This equal to 10. 1 divided.
تمام، شكرا.
Any more question?
No, you can proceed.
Which is false statement about multi-stage compression? Yeah, we're just going to help you. The correct answer here is volumetric efficiency is high. But what's multi-stage compression actually? I used multi-stage compression if you remember the curve for constant pressure. I tell you the constant pressure curve is close together from left side and far from the right side, correct? This is the profile for pressure constant. So it's good here for the turbine expansion here to obtain more expansion, and here to decrease the compression range. We need also more advantage for that, so going to use it multi-stage compression. Multi-stage compression, we use this to decrease more the range for the compression. This range is decreased. How to decrease it? Just I divide it. I don't go direct from first step to the requested pressure you need. No, I going to stages. I going to from the initial pressure to the intermediate pressure. So after that, going to intercooler. So back to left, and going to compress again to another intermediate one. So back to left by intercooler. So what happened? Decrease the compression total at the end. Let's see this one here in details. It's not this slide, but just solve this one and I will show you. It's maybe after some slide, I will show you what happened exactly for multi-stage compression. Multi-stage compressor, the isothermal compression is achieved by this famous question. No. By running compressor at very slow speed. Isothermal compression you can obtain by running compressor at very slow speed, which is almost difficult to do that, not applicable. So after some slide, we will see another question. In the case of as it's not applicable or slight difficult to make this go for reciprocating compressor to move it slowly. So what is the other option? But let's see this question. We will see later. Multi-stage compression. Here, between each compression stage, the air passes through the heat exchanger where it is cooled. Cooling the air reduces the amount of work necessary to compress. So let's see here in the curve what's happened. This the first line here, P1, and this is the required pressure you need to compress, P2, okay, to start going to compression. Please close the mic. Close mic, please. So you're going to compress from 1 to 2. This is regular, but it's better to going to intermediate partial pressure here in the middle, then going intercooler, then going to compress again, intercooler, and press to the certain pressure required. The sum of this pressure of the compression here is still, the total here is less than the direct compression from 1 to 2. Okay, so what the advantage here? The mainly advantage is going to decrease the work of the compressor, save work. This maybe describe you in the how many work saved. This work saved here. If you're going not direct, it's going like this stages. Okay. Adiabatic compression, it means exactly. Yeah. Actually, definition of adiabatic. What's the definition of adiabatic? Adiabatic, it means there is no heat transfer. There is no heat transfer. So the best answer for this one, no heat leaves or enter the compressor. This is the best answer. Capacity of a compressor is 5 meter cube per minute, refers to hello.
Decompressed air at delivery pressure.
Regular is free air. Overall isothermal efficiency of compressor defined as a ratio of isothermal efficiency. I have an answer here as a thermal to break horsepower. Any other idea? Let's see. As thermal horsepower to break horsepower. Most efficient method of compressing air to be compressed.
B.
Adiabatic, isentropic. I have to
A. Isothermal.
isothermal. Let's see, the answer is isothermal. Yes, this is minimum work. We studied this before. I described to you this before for, I don't remember last session or the last session before. This line, which is polytropic here, bv to power n equal constant. I tell you n when equal to 1, this is the minimum work you can obtain, which is referred to as the thermal. And the gamma is the maximum, 1.4 for air, which is adiabatic. This is the maximum you can obtain, maximum work. And n is in between. N is in between. Just a minute, please. I put the charger.